the algebra still, and hopefully, if my voice helps, we can start a new topic, which is vector space. But there are a few things left which we need to discuss. The last thing that we discussed was Hermitian, skew-Hermitian, symmetric, and skew-symmetric, right? And now we can say that any square matrix whose elements are complex number can be written as any G plus JH, where G and H are Hermitian. So the question is that how can we find G and H? G is half of the addition of A plus A Hermitian, and H is 1/2J of A minus A Hermitian, or in some book you might see it is written as J divided by 2 multiplied by A Hermitian minus A. We may recall that 1/J is minus J. So if we put the J into the numerator, we have to multiply everything with a minus. We have two more definitions. A is called unitary matrix. So A is unitary if A inverse is equal to A Hermitian. And A is called normal if A Hermitian is equal to A Hermitian A. Okay. For real valued matrix, the normal definition is A transpose is equal to A transpose A. What about the unitary? What about the unitary? It's defined only for complex value only. Okay, we define unitary for complex value. But normal can be defined for the real value as well. So let's see how we can use it. If A is unitary, then A inverse is also unitary. Okay, I'll give you 1 minute so I can rest. try to prove that if A is unitary, the inverse of A is also unitary. What was the definition of unitary? For A, we have A inverse is equal to A Hermitian, right? This was the definition of unitary. So, for any matrix, we have this law. So this is my any matrix, and I just replace it into the definition. Right? What is A inverse inverse? And here I have same thing. I take the Hermitian of the both sides. What is the Hermitian of the Hermitian?
The inverse of the
No. A Hermitian is?
A.
A.
Same.
So here I take the Hermitian of both sides. There is one more approach which we can use, and this approach needs to have this knowledge. The inverse and Hermitian are interchangeable. So which means that in the equation star, I can write that A inverse is equal to
inverse of A Hermitian.
Inverse of no, I was doing something else. Ah, sorry. I can use this and I write this equation as I take the inverse of both sides. I take the inverse of both sides. So what I have is I interchange these two. And look what I got. The inverse of this matrix is equal to the Hermitian of this matrix. So A inverse is unitary. So there are two ways. I can do that in some books, like the Book of Strength. They use this one. And in our book, they use this notation. Both of them will end up into the same proof. A very important property is if A is unitary, the determinant of A is 1. And I can guess where the unit term comes from. if A is unitary, again, a question for you for 30 seconds to think. You don't need to write this green writing because I will erase it. Is A normal true? If the answer is no, why? If the answer is yes, why? So you have to choose. Hassan, you will answer this question. What was your name? Anna. Okay. This is also your first lecture, right? Last week we were supposed to talk after the image processing class, but we didn't come to talk.
All right. Yeah.
I mean, anytime you can.
Yeah, so.
And you can even come to my office.
Mm-hmm.
All right, Ike. You are also thinking, right? I mean, Hassan will answer, but take it. Hassan, you have a 50% chance of giving the answer correctly. Is it normal or not? Okay. What is the definition of normal?
A times A remission becomes A remission times A.
Very good. So why do you think it is?
I'm trying to figure out.
Okay. Mike?
Well, yeah, I think it's normal
Why?
because since the A inverse is equal to A Hermitian, then
Excellent. Excellent.
it's just basically the same thing.
Very, very true. If A is unitary, then A Hermitian is equal to A Hermitian A. You should know that already A Hermitian is equal to A inverse, which is equal to I. Right? If A and B are unitary, then AB is also unitary. As usual. Why? Why do we have if AB, I mean I hate this word, if AB is unitary, are unitaries, then A multiplied by B will be also unitary. Now this type of good morning. These type of questions are easy approach to solve is this. Look, if AB wants to be unitary, it means that AB Hermitian should be AB inverse, right? This is the definition. So, how can I understand this is true? The easy form is that you know that for any matrix, A multiplied by A inverse is I. You must, in this course, you must also check A inverse multiplied by A is also I. By A, I mean any matrix. Here, A is AB. Why we need to do that? Because in 2 chapters, when we are talking about pseudo-inverse, you see that we have actually definition of right inverse and left inverse. And when we are using this notation, we mean that right inverse and left inverse. Okay? So let's see what we are doing it. We are doing it in this form. We check if AB multiplied by AB Hermitian will result into the I. This is equal to AB Hermitian. We know that we interchange these two. So it's B Hermitian, A Hermitian. Because B is unitary, this is I. So it's A emission. A is unitary, so this is I. So from the right, it's done. From the left, AB Hermitian multiplied by AB is B Hermitian, A Hermitian, A, B. Again, A is unitary, so this is I. So we are left with B Hermitian B, which is equal to I. So the proof is complete. A matrix is normal if it is symmetric or skew symmetric or what else?
Hermitian.
Yeah, exactly. Or skew emission or there is one more which we learned today.
Unitary.
So if you are any of these, definitely you are normal. What was the definition of normal?
A Hermitian.
A Hermitian is equal to A Hermitian A, or A transpose is equal to A transpose A. If you remember, we were talking about orthonormality when we were talking about vectors. Let's see how a matrix is defined to be orthonormal. I write this A capital in the sense that this is not matrix A. This is like one matrix is, okay? But this A means that this, I'm talking about matrix A. A is orthonormal if A belongs to R and this is a matrix A transpose is equal to A transpose A. What is this?
I?
What's this definition?
No.
Normal.
Normal.
But so the normality is here, and then if this is equal to 1, okay, we call it orthogonal. Then the determinant of A is plus minus 1, and as you can guess, A inverse is A transpose, right?
So orthonormal is just the same as unitary except for if it's within real numbers?
If you're a real number, we don't define unitary. Unitary is only for complex values.
Okay.
If given A and B are a square matrix in real and are orthonormal, then AB, A inverse, A transpose are also orthonormal. And for any orthonormal matrix A, we have the second norm of AX, include the norm of AX to be included in the norm of X. Of course, because we want to have the multiplication to the value. It's in Rn, where A is in Rn by n. And if A is an orthonormal matrix, we will use this thing that I will write in a few seconds. If we multiply A by X and A by Y and then do the inner product, it's the same as the inner product of X and Y, given that X and Y are Rn. Pick up one number on this from here.
5.
5. Anna, pick up one number.
2.
2. Hassan, pick up one more number. 4. 3, pick up the last number.
3.
Okay, I will put the question, the end of the chapter question, and these 4 questions are your homework questions. In the next lecture, I will solve the question number 1 and 6 for you. So you will do question 2, 3, 4, and 5. Typically, at the end of each chapter, we have around 6 questions, and I will assign you 3 to 4. Depends on how repetitive some of the questions are. Okay, and usually we randomly pick, like you decide. We start the new chapter, which is talking about vector space. Mainly we will talk about independency of the vectors that we have, talk about the dimensionality of the vectors that we have. They are talking about that, some properties of vectors, do some addition, subtraction, and so on. You might have seen some of the terms, but now we will describe them in a more complex and complicated form. Let's put it in that form. Or let's say we will describe it in a form that you can use this type of writings in your research paper. Like a very simple task, but we are seeing it how proficient we can write it down, right? So vector space is the title. We do a few definitions at the beginning. a field is a set of a field and represented by F usually is a set of scalar which is closed to addition and multiplication. In other words, now let's see that what we mean by being closed. We will use this word quite a lot. What we mean by one operation or one set is closed over one operation. The meaning of this is if A and B belongs to F, close to addition means that then A plus B is also in the F. And the second one, if A and B are in the F, then A dot B is also in the F. So this is the meaning of the clause. And then we can actually derive some series of properties which I put all in number 3, and we write it in this form. If A, B, and C belonging to F, if A, B, and C are belonging to F, A plus B is equal to B plus A multiplied by B is equal to B multiplied by A. A plus B plus C is A plus B plus C. A multiplied by B multiplied by C is A multiplied by BC. You don't have a proper plan. A multiplied by B plus C is AB plus AC. We have a zero element or sometimes this is called a natural element or addition. Which means for any A belonging to F, there exists a zero belonging to F where A plus 0 is equal to 0 plus A is equal to A. And natural element for multiplication can say for any A belonging to F, there exists a 1 belonging to F in a way that A multiplied by 1 is equal to 1 multiplied by A is equal to A. This natural element for multiplication is also called identity element. I erased this part because I need these properties. We need to do a few tests together. I mean, verbal tests. So I just erased that part. And I use green to continue. Number 6. So for any A belonging to F, there exists a B in F such that A plus B is equal to 0. And we show that B is minus A. And this is defined to be, do you know what is it called? What is the name that we use for B?
Negative?
Or inverse?
Inverse element for addition. Where it is called inverse element for addition. You're all right in the daily life, we also call it a negative of a number. It's called an inverse element for addition. And as you can guess, we have inverse element for multiplication. The 7th one is for any A belonging to F, there exists a B which is in F, and AB is equal to 1. And we say that B is equal to 1 over A or A inverse. And it is called the inverse element for multiplication. So B is called the inverse element. Now, as I said, let's do some verbal test. I'll finish writing if you're writing. What's your name?
Lower.
Laura. I mispronounced your last name. I don't want to try. Okay, Laura, let's start with you. So I give you, so F is a set of number, okay? So I give you a set of number, and you tell me if this set of number is a field or not. So how do we understand if it is a field? Here we are, lots of conditions you have to check. If one of them fails, that's enough to say no, it is not a field. Let's start with something big, real numbers.
Is a field.
It is a field. Why? Because addition of any two real number is a real number, and multiplication of any two real number is a real number. If these two is valid, we know that number 1, number 2, number 3 will be valid. Let's check number 4 and number 5. Do we have any element which if we add it, we will get the same thing? Yes, we have number 0. Do we have any element if we multiply, we will get the same thing? Yes, we have number 1. Now, very tricky one is number 6 and number 7. Do we have the inverse for the addition? Do we have a negative of numbers in real number? Yeah, we do. Do we have the inverse of the numbers in real number? Yes, we do. So, you know that if number 6 and number 7 exist, it means that number 5 and number 4 are automatically verified.
What about 0?
Because if you go to the infinity, we can say infinity exists. Yeah, we don't have any bound. Now, Ike, complex numbers. complex number is also a field because all the conditions are being verified. All conditions are being verified. All right? Now, numbers. You tell me natural number. You know natural number? What are the natural numbers? We show them with n. Natural numbers, what are they?
Integers?
I don't know, you tell me.
Positive
Sorry?
integers.
Positive.
So tell me, I want to write them down.
1 to infinity with
Yes.
nothing in between. Yeah.
And it goes to infinity, as is both said, positive integers. So they start from 1. If I pick any number, Anna, if I pick any number in integer, I mean in here, and I add it with any number in here, do I get any number in here? Yes. What about multiplication?
Yes.
Yes. Okay, Hassan. Tell me number 1, 2, 3 are number 1, 2, and 3 valid for natural numbers? Yes, they are. They are. Because basically we know that number 1, number 2, number 3 will be valid if these two are valid. Mostly. I can come with you a counterexample. Now, Preet, tell me if n is a field.
No,
N is not a field. Why it is not a field?
it doesn't have a zero element.
It doesn't have a natural element for addition. And basically it fails because of number 6 and number 7. Because we do not have the inverse element for addition. Like I do not have any number which I can add to this natural number, which is inside the natural number, and I get 0. Similarly, I do not have any element inside natural number.